So you guys saw what is the motional EMF for linear motion, correct? So we do the same thing for circular motion. So what you have, see, you have uniform magnetic field and you have some metallic rod which is moving in the circular motion, right? So we need to calculate what is the motional EMF because of the motion of the rod in a circular motion. Now you have the magnetic field to be B, correct? And then radius of the particular metallic rod, let's call it as R. Alright, it's moving with the angular velocity of omega because it's in circular motion, correct? Now last year, if you guys remember, you learned a relation between angular velocity and linear velocity, right? So the relation was v is equal to omega into r. That is, linear velocity is angular velocity times the radius. Now these are the things what we might need here to calculate the motional EMF. All right. Okay, see, now what you have, for a very small value of the radius, let's say dr, it induces a small EMF dE. So what we need to do is we need to integrate the whole thing and get the total EMF. Okay, so we have, now see, last video what you guys saw, E is equal to BLV, correct? That was the thing. Now in place of L, we have this small value dr, correct? Because that's what it's changing. So we have dE is equal to BV into dr. Now when you're integrating, we need the limits. Limit will be from 0 to capital R, because that capital R is the total radius. Okay. Now what we have, dE, so when you integrate dE, you get E, right? So E is equal to integration from 0 to R, B, see what was V, omega R, substitute that here. So we get B omega R dr. Okay. Now B omega is constant, so if you keep it outside, you'll get this as B omega integration of R dr from 0 to R. Okay. So if you integrate that, you get R square by 2. If you substitute the limits, so you will get the answer as half B omega into R square. So this is the motional EMF of any metallic body or any object which is moving in a circular motion in a uniform magnetic field. Okay, so I'll just repeat the whole derivation, like what it has, what is happening in the derivation. So you have the magnetic field, you have a metallic conductor rotates. All right, so it rotates with the speed of omega, or the angular velocity, by the formula E is equal to BLV. So we have dE is equal to BV into dr, because dr is the small radius what we are taking. So when you integrate this, the limits will become 0 to R. So you have dE equals integration from 0 to R BV dr. Okay, so once you change the linear velocity to angular velocity and then apply the limits, you will get the answer as half B omega into R square. All right. So this is the motional EMF for the uniform circular motion, and E is equal to BLV is the motional EMF for linear motion. All right.